Hello everyone and welcome to the class of Econometrics 1, Econ 331, lecture number 22. And in today's lecture we are going to study about the multicollinearity. So before starting with the multicollinearity, first we need to understand the assumptions of classical linear regression model. And a typical classical linear regression model has a dependent variable, let's say yt, and a number of independent variable, let's say alpha plus beta 1 x1 plus beta 2 x2 and an error term. So this is our typical regression model. This yt is our dependent variable which depends on x1 and x2, but this can have certain problems. There are certain assumptions related to this linear regression, and one of the assumption is that the variable x1 and x2, these should not be perfectly related to each other. These should not have a linear relationship. Then we have certain other assumptions, that is the variance of these coefficients. They should stay constant over time and should not vary as we increase the variable x1, x2, as we take more and more values, the higher values of these. Then there is another problem or another assumption that is associated with the classical linear regression model, is that the error term of uh, the error term I and the error term, let's say j, they should not be correlated, or the error term in different time periods should not correlate with each other. Then again we have some problems related to the misspecification. We take the wrong regressors of x1, x2 that are not actually related to yt. So these were the some of the major assumptions that we have taken with classical linear regression model. Now from now on we will try to cover what will happen if any of these assumptions is violated. And if these assumptions are violated, we can have the problems of multicollinearity, we can have the problem of heteroscedasticity, the problem of autocorrelation, and we may misspecify the model and how we need to correct these models. Now let's say if the two independent variable, that is x1 and the x2, they are related with each other. If they are related with each other, then the covariance of these two will not be statistically equal to 0, and they may have a linear relationship. This linear relationship can have two forms. One form is called perfect multicollinearity, and the other is called imperfect multicollinearity. So in this lecture we are going to discuss both the perfect multicollinearity and what are the consequences of the perfect multicollinearity. Here we have the sequence of this lecture, the contents. First we introduce the problem, then we will discuss about the perfect multicollinearity and what consequences that are related with it. Then we will move on to the imperfect multicollinearity and the consequences that occur because of the imperfect multicollinearity, and then how we are going to detect whether a model, a regression equation that has the issue of the multicollinearity, what is the method of detection and how we can resolve if we have a multicollinearity in a model, and whether that multicollinearity is actually problematic or not. So we will be discussing that in our model. Let us understand the problem of multicollinearity from an example. We have a typical model, let's say that yt is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus u. So this is our typical ordinary least square model. Now we may have sample values for x2 and x3. x2 has the value of 1, 2, 3, 4, 5 and 6, whereas the values of x3 are 2, 4, 6, 8, 10 and 12. Now the model may have multicollinearity if x2 and x3 are related, and we can see that from the values that x3 is the square of x3 is actually equal to 2 multiplied by x1. So we can find all the values of x3 as a linear relationship of x2. If x2 is 1, 1 multiplied by 2 is equal to 2, and that is x3. 2 multiplied by 2 is equal to 4, 3 multiplied by 2 is equal to 6, 4 multiplied by 2 is equal to 8, and so on up to the last 6 multiplied by 2 is equal to 12. So these are related. x3 can be basically given a linear equation such as x3 is equal to 2 times the value of x2. So there is a perfectly linear relationship exists. Or we may also say that we may say that there is a perfect multicollinearity if we can write any equation in this form. Let's say sigma 1 x2 plus sigma 2 x3 equals 0. If we can write the independent variable in this form, then there is a perfect multicollinearity. If you cannot write it in this form, then there is imperfect multicollinearity or no multicollinearity. So we can write our equation by converting it into this form, that is x3 minus 2x2 is equal to 0. So the coefficient of x3 is 1. 1x3 and minus 2, these are the coefficients. Minus 2x2 equals 0. So there is a perfect multicollinearity in our example. Now there is also one case in which this can be satisfied, and that is called the trivial solution. But we are not in the absence of the trivial solution. If this situation is true, then there is multicollinearity, otherwise there is no multicollinearity. Then again, we can also have examples where we have more than two independent variables. Let's say that we have 5 independent variables, and these independent variables are x1, x2, x3, x4 and x5. So whether these variables have perfect multicollinearity or not, again the condition is that if we can write it in the form such as sigma 1 x1 plus sigma 2 x2 plus sigma 3 x3 plus sigma 4 x4 plus sigma 5 x5, and all of them are equal to 0. In this case, then we can say that there is a perfect multicollinearity. And this example can be best understood by using and if we understand the dummy variable trap. For example, if x1 is to be the intercept, so let's say that x1 is equal to 1, and if this is true, the rest of them will not be true. That x2, x3, x4 and x5 are to be seasonal dummies for quarterly time series data. Let's say x2 takes the value of 1 for the first quarter, then all of the remaining will be 0, and x3 will take the value of 1 for the second quarter, and then um, the remaining sigmas, they will be 0. So summing them all up, we will then get an answer equal to 0. That is a dummy variable trap. So similar concept is applied here. It is also identical to the dummy variable trap. So what happens if we have a perfect multicollinearity? What will be its implications on the model? Again, let me take this model. Y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus ut. So this is our basic model, the basic regression model. And if x2 and x3 are perfectly related such that we can express them in the form of a linear relationship as x3 equals sigma 1 plus sigma 2 x2, and sigma 1 and sigma 2 are they are basically constant. Now we can express x3 as a linear function of x2 in this scenario. So what will be the consequence of such a model? So what we can do is that we substitute the value of x3. We can substitute the value of x3 over here and see what can happen. So our model will become y is equal to beta 1 plus beta 2 x2 plus beta 3, and replacing the value of x3 we get sigma 1 plus sigma 2 x2 and the error term ut. Then rearranging, what we get is y is equal to beta 1 plus beta 3 sigma 1 plus beta 2 plus beta 3 sigma 2 x2 plus u. So we have eliminated x3 entirely, and rewriting the whole equation, we are left with this equation. And we can also see that redefine these coefficients, because beta 1 plus beta 3 sigma 1, all of these are constants. So we give it another name. We call this theta 1 plus again beta 2 plus beta 3 and into sigma 2. We give this another name, sigma theta 2 x2 plus u. So basically we can rewrite the entire equation only in terms of a single variable x2. We have eliminated x3 and rewrite this in such a form. Now we are able to estimate using the ordinary least square method, and that will be perfectly fine. We can estimate theta 1 and theta 2, but we cannot estimate the values of beta 1 and beta 3 and beta 2. We cannot estimate them. We can perfectly estimate theta 1 and theta 2, but we cannot find the values from them. Why? Because let's say that if we have theta 1 is equal to, again I'm writing this whole equation, beta 1 plus beta 3 sigma 1 and is equal to beta 2, again from this equation, plus beta 3 sigma 2. Now how many unknowns do we have? We do not have the value of beta 1, beta 3 and beta 2. So we have 3 unknowns and 2 equations. So it is not possible for us to determine the value of beta 1, beta 2 and beta 3 because we have more unknowns than the number of equations, and therefore the value of beta 1 and beta 2 and beta 3 are undeterminable. We cannot determine these values. So in such scenarios, if we have a perfect multicollinearity, we better need to estimate, we need to take only one of them and re-estimate our equation in this form as theta 1 plus theta 2. Basically we need to take any of the two variables if they are perfectly linear. So why take both of the variables? Only take a single variable and let it determine the value of y rather than taking both the variables. Otherwise, if we are taking both the variables, we have more unknowns and we cannot determine the value of those coefficients. Summarizing the perfect multicollinearity, it is a very serious problem, but the good news is that this does not occur in real life. Mostly in the real life, the data has imperfect multicollinearity. So such a strict linear relationship does not exist in reality. And if it exists in reality, then another good news is that it is easily correctable. One method that we have explained is that we drop one of the variable and try to explain it with the other variable. And another method is such as the correcting of Dimitrov variable. That is, we may include logrammatic forms of the variables such as ln x and ln x square in the same equation. But the more relevant question and the real problem is that how to deal with the more common cases of imperfect multicollinearity. And we are going to examine in this current section, we are going to examine the imperfect multicollinearity, what it is and how it affects our model. So let us start with it. An imperfect multicollinearity exists when the explanatory variables in an equation are correlated, but this correlation is less than perfect, or we may say that it is less than the absolute value of 1. Means that we may also have perfectly negative correlation or perfectly positive correlation. So it should be less than 1. An imperfect multicollinearity can be expressed in following way, that when we are studying the relationship between two explanatory variable in an equation, and for example we have x3 that is equal to x2 plus v. Notice that now not that we have added some random term v, which was previously not present in the perfect multicollinearity. In perfect multicollinearity, there was no random term, rather than x3 was some perfectly linear, had some perfectly linear relationship with x2. Now there is an imperfect linear relationship. There is some random variation attached to it. Then we can also treat this v as a random error term in this exact relationship. Then if v has a non-zero value, we can obtain the ordinary least square estimates. On practical note, in reality, every multiple regression equation will contain some degree of correlation amongst its explanatory variables. Whatever variables you take as the independent variables and you try to run a correlation test between them, you will find that they are at certain degrees they are correlated with each other. So the time series data, for example, frequently contains a common upward time trend that causes the variables of this kind to be highly correlated. If you take time series data and two variables, for example, and let's say you are taking GDP and you study GDP for all the countries, GDP somehow will be increasing over time. Similarly, if you are taking the inflation rate is or you say the price level will always be increasing for those countries. So if you check a correlation between those two variables, you will find that there is a certain degree of relationship between the two. But the problem is to identify whether the degree of multicollinearity observed between these variables is high enough to create a problem for us. So before discussing what we need to examine is the effect of the imperfect multicollinearity in our ordinary least square estimate. So in general, the imperfect multicollinearity exists among two or more explanatory variables. Not only are we able to obtain the ordinary least square estimates, but these will also be the blue, or we may say the best linear unbiased estimates. However, the blueness of these should be examined in more detail. Implicit in the blue property is that the efficiency of the OLS coefficient. As we shall discuss it in the later section, the OLS estimators are those with the smallest possible variance of all linear unbiased estimators. Imperfect multicollinearity affects the attainable value of these variances and therefore also the estimation precision. So using a matrix solution, if we use the matrix solution, the imperfect multicollinearity implies that one of the column of the X matrix is now an approximate linear function of one or more of the others. So therefore, let's say that if we have matrix X dash and X, this will be close to singularity, which again implies that its determinants will also be close to zero. So as stated earlier, when we are forming the inverse matrix, such as the inverse matrix, we multiply by the reciprocal of this matrix, which means that the element and particularly the diagonal element of this matrix will be large, and because of the variance of beta hat is given by this variance of beta hat can be found as the variances and consequently the standard errors of the ordinary least square estimate will tend to be large and when there is a relatively high degree of multicollinearity. In other words, while the OLS provides linear unbiased estimators with the minimum variance and the property of these variances are often substantially larger than those obtained in the absence of multicollinearity. So in order to explain this in more detail, consider the expression that gives us the variance of the partial slope of a variable. Let's say we have xj, and which is given by in case of if we have two explanatory variables, it is given by the variance of beta 2 hat that is equal to sigma square summation x2 minus x2 bar into 1 minus r square, whereas it is about the correlation, and then variance of beta 3 hat is equal to sigma square summation x3 minus x3 bar, and we should take square in both the cases, 1 minus r square. So r square is the sample correlation coefficient between x2 and x3. R square is basically the correlation coefficient between x2 and x3, and I've discussed that earlier in while discussing the ordinary least square, that when we have two variables, r square shows the correlation between them. So this will lead to an increase in the variance, and therefore also it will increase in the standard errors of the ordinary least square estimation. So extending this to a more than two explanatory variable, the variance of bj, that will be then given by the variance of bj that will be given by sigma square and summation xj minus xj bar whole square into 1 minus r square, and this r is of j. So this is a most generalized form. Let me write this equation a bit clearly because it is out of the screen. Summation xj minus x bar j whole square into 1 minus r square. And we know that r square is the measure of goodness of fit that we usually calculate while estimating our coefficients. So Rj is the coefficient of determination from the auxiliary regression of xj and all other explanatory variables in the original equation. And the expression again can be rewritten as variance in bj is basically equal to sigma square divided by summation xj minus xj bar whole square, and multiply that by 1 over, we are just separating the r square effect out of it. Then the second term in this expression is called the variance inflation factor for xj. So this is inflated the value of this is inflated by this much. Therefore, we are calling it the variance inflation factor, or in short, we call it as VIF. And this VIF in simple is written as 1 minus 1 over r square of j. It is called the variance inflation factor because high degree of intercorrelation among the explanatory variables will result in a high value of r square, and which will inflate the variance of bj. So let's say that if if r square is equal to 0, then the value of VIF will equal to 1. If this is equal to 0, the whole value will equal to 1, because 1 over 1 minus 0 is equal to 1 over 1, and finally 1. So we may also present it by table for the value when we have r square is equal to 0. We may have VIF equal to 1, and when we have r square is equal to 0 0.5, VIF will equal to 2, and so on up till we reach to the r square 0 0.99, where the VIF is equal to 1000. So higher the VIF means higher the value of higher will be, if higher value of r square, then we will have a greater value of VIF. So there is a general principle, that is the VIF values exceeding 10 are generally viewed as evidence of the existence of problematic multicollinearity, and that occurs when we have r square is equal to 0 0.9. On that, the value of VIF is equal to 10. So whenever in a regression analysis we have multiple explanatory variables, and we may observe a higher r square, usually we think that r square is a good measure, but it is not always good. And one of the reason is that because of the multicollinearity, the value of r square can increase, and whenever the value of r square is greater than 0 0.9, we should be very careful for the presence of multicollinearity. If there is a multicollinearity, we should resolve for it first. So let me repeat it again. Values of VIF exceeding 10 are generally viewed as evidence of the existence of problematic multicollinearity, which for that we have the value of r square greater than 0 0.9. And in conclusion, the imperfect multicollinearity can substantially diminish the precision with which the OLS estimators are obtained. And this obviously has more negative effects on our estimated coefficients. One important consequence is that the large standard errors will lead us to confidence interval for BJ parameters, and those parameters will not be reliable. Therefore, the t statistics that we also obtain because of the high standard errors will also be inflated, and the multicollinearity raises the denominator of the statistics that causes the value to fall. Therefore, we might have t statistics that suggest the insignificance of the coefficients, but this is only a result of multicollinearity. Also, you should know that there in the existence of the multicollinearity does not necessarily means that the t statistics will be small. This can be because the variance is also affected by the variance of xj that we presented in these equations, and the residual variance of sigma square, the multicollinearity, affects not only the variance of the OLS estimators but also the covariances. So therefore the possibility of a sign reversal arises, and also when there is a severe multicollinearity, in addition to the deletion of just a few sample observations, can change the estimated coefficient substantially and causing unstable OLS estimators. So the consequences of the imperfect multicollinearity can be summarized in the following 4 points. The first consequence of the imperfect multicollinearity is that the estimates of the ordinary least square may be imprecise in the sense that larger standard errors will lead us to a wider confidence interval. And since the second one is again related to the first one, having larger standard errors will give us smaller t-statistics. And when we have smaller t-statistics, the coefficients may fail to attain statistical significance. We may reject the correct relationships. And then again, it can also cause the signs to be opposite to those expected. And finally, the fourth problem that is associated with it is that if we add or delete a few observations from our data, this may result in substantial changes in the estimated coefficients. So these are the problems associated with the imperfect multicollinearity. And in the next session, we are going to discuss how we are going to detect such types of multicollinearity. And if we have these types of multicollinearity, how can we resolve the problem? So hope you have understood up to this part. And if you have any question, do ask in the comment section. Thank you very much.